So in the previous video, we had this setup where we had n times some constants here, and I can't remember what constants, subscripts they were. It doesn't really matter. And let's just say we add up all of our constants, and they came out to being 2. All right, maybe this is 0.5, 1, 0.5, so it comes out to 2. And then we have this set up again, maybe more constants. We have 20 constants out there, and all of our constants add up to 1. This example I'm working would work with any constants, but I'm just picking simple ones because it's easier to learn with simple ones, I think. So if I have that, then I really have n times 2 in one case and n times 1 in another. Well, n times 1 is just n, and n times 2, mathematically we would like to write that as 2n because we put the constant in front of our term here, our variable. So let's roll with this a little bit. I got a new tool here. Or I found this graphing calculator. It was the first one showed up on Google search when I did online graphing calculator. This is a little bit better than typing our equations into Google. So I want to use this. Let me come over here. We had n, but I have to put x because this is a y equals x thing. And maybe if I poked around here, I could figure out how to do an n. But we'll say x, and then we'll say 2x. And remember, we're not worried about all the negatives out here because we know we're only going to have a positive number of items in our array. We'll have an array of 5 items or 10 items or 100 items or 100,000 items. So we're really just worried about this positive range here on the x, and then we're not going to worry about any negative y because I don't know any algorithms that take negative time. That'd be kind of cool. You could roll back the clock on your life. Like, here I'm going to feed this 100 elements, and I just shaved 100 years off my life. Well, if I did that right now, I wouldn't exist, actually. So I'd exist in a previous life. How about that? So I'm just going to drop that down there. Let's ignore all this negativity. We should really get the negativity out of our life, so I like that anyway. Okay, we have, let's see, what color is that? That looks black. All right, so we have 2x in black. I'll just draw that here. 2x. See 2x in black. And then this looks kind of orangish, but I don't have an orange, so we'll just say it's red. Maybe it is red. All right, this is x. All right, but I remember, we don't like x. We want to do n because that's what we're going to use. We had to use x on this calculator because that's what the calculator wanted. So we have n and 2n. Let's look at how these guys are growing compared to each other. All right, obviously this one's going faster, and if we're in the same fraternity and you want to grow faster, in algorithms we don't want to grow faster, but if you want to grow faster, then a 2n car is faster than an n car. That's true. But if I can get in a different fraternity, then that's better, n squared, quadratic. Except when we're talking about algorithms, then I don't want to be in the quadratic. I want to be in the linear. Anyway, I digress. Let's chart this out a little bit. I'm going to put n here. And hopefully this is going to be kind of obvious what I'm doing. And you who have taken up to calculus, that's not required for this playlist, but you're going to probably see this from a mile away. So let's not stress. We have n. So I'm going to put 2n out here, and then we're going to put n right here. And I want to see how these guys are growing compared to each other. Well, if n is 0, then the time our algorithm is going to take is 0. And then if n is 1, then our time will be 1. And this could be 1 second, 1 millisecond, 1 microsecond, 1 clock tick. Doesn't matter. It's all relative. Faster computers don't make your algorithms any faster. Let's see. 2, 3, 4, 5. Hey, look, this is simple. Nice linear growth. So on and so forth. Let's do 2n. Okay, I'll switch to black here. Well, 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 6, 8, 10. Love counting by twos. I have loved counting by twos ever since grade school. Okay, let's look at the growth here. Alrighty. From 0 to 1, how much did n grow? Well, 1 minus 0. 1 minus 0. It grew by 1. Go figure. All right. Well, 1 to 2. How much did this function grow? Well, 2 minus 1. Hey, it grew by 1. 3 minus 2. It grew by 1. Oh, look at this constant growth of 1 there. All right, the growth of our red function here is 1. And if you calculate your derivatives, you're obviously going to be like, yeah, just take the derivative and it leaves you 1, Jamie. Good job. But if you don't understand that, well, here we go. Brief brief intro. Hey, how much did this one grow? All right, how much did 2n grow? Well, let's see. Grew from 0 to 2. It grew 2. And then from 2 to 4, well, 4 minus 2 is 2. Hey, from 6 to 4, so 6 minus 4 is 2. It's growing 2. All right, it's growing by 2 every step here. We're growing by 2. So we'll put the 2 here. And we'll put a ratio here. I want to say how much faster is this function, this 2n growing, over the n? Well, every time that the 2n steps, it grows by 2. Change our 2 to black to be consistent. And then our ratio, I'll just change that to blue. So this grew by 2. The 2n grew by 2. And the bottom one grew by 1. Well, 2 divided by 1 gives me 2. All right? This function is growing twice as fast as that function. Well, what if I change this function up? Let's say instead of 2n, we did 4n instead, and I updated all these values. Well, really what's going to happen is we'll see that these hops change to 4, and that's going to change this value to a 4, and then 4 divided by 1 is going to be 4 down here. So the 4n function is growing 4 times faster than n. All right, well, if I change this to 8, it'd be 8, or if it's 16, 16, or 13.5, it'd be 13.5. The key concept to take away from this whole discussion is that these are constants, and these constants are not 0. All right, and they're also not infinity. Let me show you another one here. In fact, this could be simpler. If we had 4n over n, I don't have to lay out all these numbers like I did. I could just say, well, one's growing at 4n, another one's growing at n, and n divided by n, that cancels out and leaves us a 1 down here, which really just leaves us with a 4. All right, so I didn't have to do all this hop, hop, hop stuff. It's good intro stuff if you're new, but really we're just left with this constant here, and that constant is not 0, and it's not infinity. Let's look at a different case. Say, don't blink, I'm going to erase some stuff. Remember we had our race, and you had a car that I believe went 4n, and then I came into the party and said, you know what? I don't want an n. I want an n times n. All right, n times n. So my car is going to go n times n. You're going to go 4n. And at the beginning, you're like, yeah, I'm going so much faster because before I only had a 2n, and now I got a 4n. I'm so happy. And I'm just smiling like, you just wait. I'm going to catch up to you, buddy. And when I catch up to you, I'm going to sail right past you. So, all right, you're going 4n. And I'm going n squared. That's what n times n is. It's n squared. But I really want to write this out how I have it up there. So I'm going to write n times n times n. And then, oh, look, these n's cancel. So we'll just cancel those out. And what are we left with? We're left with 4 over n. Well, all right. Let's say we go 1 mile. All right. At 1 mile, that's going to be 4 divided by 1 down here. So 4, okay. Let's go 2 miles. 4 divided by 2 is going to be 2. Let's go, easy numbers. Let's go 4 miles. 4 divided by 4 is 1. And we'll go 8 miles. That's going to be 0.5. We'll go 16 miles. That'll be 0.25. Do you see how these values are decreasing? And they're eventually going to decrease down to 0. And 0 means that my car is dominating your car. You're in a different fraternity. You're in a different order of growth. Yeah, from the get-go, you're going 4n, but I just dominated you, and now at 0. Well, let's take the reciprocal of all this. Okay, meaning, I wrote the ratio. I conveniently chose to put your value over my value, so that we could see you get dominated. But let's flip this. Instead of 4 over n, I'm going to do n over 4. All right, let's go 1 mile. 1 divided by 4, 0.25. 2 divided by 4, we'll go 2 miles. It's going to be 0.5. 3 miles will be 0.75. So on and so forth. 4 will be 1. 8 will be 2. Easy numbers. 16 will be 4. I guess I could have done 12. That would have been 3. See how these values are increasing? And they're going to keep going and going to infinity. Okay, another mathematical way of saying this is that we diverge. All right? Meaning, I just dominated you. My car was going n squared. Yours was going 4n. We cut out one of the n's. And I'm growing at a whole new order here. way faster than you. My fraternity, as far as speed is concerned, is higher than your fraternity. But you're smiling, thinking, well, Jamie, this is really a game of golf when it comes to algorithm. We want to be in the lower fraternities. But for now, I just want to illustrate, look, we're not in the same fraternity here. We got infinity one direction, we got 0 the other direction, no dice. But when we were in the same fraternity, meaning you were going 4n and I was just going n, we converged to a constant, which is a big deal. In this case, we'd converge to the constant 4, or you could be going 16 times faster than me. We'd converge to the constant 16. Once we get a constant, which is not 0, and we don't diverge to infinity, we know we're in the same order of growth, meaning we're in the same fraternity, and that's what really matters. It doesn't matter what these constants are. Remember, at the beginning of the video, I had all those constants. Constants 22 plus constant 8 plus. I don't care what these constants are. All right? The thing we care about is that we're in the same fraternity, the same order of growth. We're going to use that throughout the rest of this playlist. But just stop there and let your brain kind of chew on that for a bit. I'll see you in the next video.